Hello and welcome back to the second video on differentiation. Today we're going to look at a photograph of a car and try and determine its speed. So over here we have a red hot Ferrari Formula 1 car. This thing can go up to 330 kilometers per hour. So what is the speed of this car at the moment this photograph was taken? Suppose you had an infinite amount of time, infinite amount of paper and pencil. Would you be able to work this out? And the answer is no. But I think more interestingly, why is the answer no? What is stopping us from working this out? That is the question I want to answer today. So if you look over here, this is a graph of what we went through in the last video of an apple falling from a tree. So just a quick recap. So the apple is actually falling from the tree. Although we are going upwards in terms of the graph, the apple actually is falling downwards towards the ground. So the direction is kind of opposite. Okay, so back to the question, why can't we find the speed of a car from a photograph? Okay, that question is the same as asking what is the speed of the apple at this exact point in time. If I had a camera as well, I took a picture of the apple as it is falling from the tree. What is the speed of the apple at that point? Okay, and perhaps now with a graph, it is a bit more clear on why we cannot find the speed, and that is because we actually need a second point. Why is that so? Because to find speed, we actually need to find what is the distance traveled divided by the time taken to travel that distance. Okay, so we need a change in distance over a change in time. And if you look at this carefully, hey, isn't that rise over run? And you're right. To find the speed of an object is no different from finding its gradient of the distance speed time graph. Yes, so we are really interested in the gradient of this point over here. And some of you might be thinking, hey, if you want the gradient, you should draw the tangent line. And I say that is a good idea. Okay, so let's suppose that a bit of background on how we got the orange graph. Say, as the apple is falling from the tree, we took, maybe we have very accurate sensors and we have stopwatches, and then we recorded 5 positions, right, in time and in distance, and we plot them out. So here's point number 1, point number 2, 3, 4, and 5, for example. Okay, and then we use a French curve or a flexible ruler, and then we drew a smooth orange curve over here. And now we want to find the tangent to, say, this point over here. Yeah, so when we draw the tangent line, yes, we get 1 point already. So what I need, remember, to find the speed is another point. I need 2 points, remember? So I need one of these purple points, and ironically, we do not have those points because the tangent to the curve only touches the curve at one single point. And to get another point, one of these purple points, you probably have to make a guess. And then when you make a guess, it's an approximation, it's an estimate, and then maybe it's not so accurate. Yeah. So I will say that, hey, we don't have a very good way of determining the gradient of this tangent line. And some of you might be catching on very fast. You'll be thinking like, hey, wait, you have 5 points on this graph. Why don't you just use any 2 of the points? And I'll say that is, again, a good idea. Yeah. Say we have these 2 points over here, one green and one red. Okay, then what do we do? So let me go over to Desmos and I'll try to show you. Whoops, let me remove these things first. Okay, so we have a green and a red point. I don't know if you can see the red point. Let me zoom out a little bit and a bit more. Yes, there you go, right? The green and the red point. Say we want to use these 2 points on the graph. Okay, and if I join them together with a straight line, yes, if I took the change in distance over the change in time, I'll be finding the gradient of this black line. Yes, but if you remember, the actual speed, right, is the tangent to the green point itself, which is the red dotted line. And you find that, hey, the gradients are not really the same, right? So using any 2 points on the graph does not give a good approximation of the actual gradient of the graph at this point, at this green point over here. Okay, so right? That is not a good approximation. So what do we do then? So here's where Sir Isaac Newton and Gottfried Wilhelm Leibniz, right, discovered. They discovered that, hey, you can use 2 points on the graph, but all you got to do is bring the 2 points closer and closer to each other. We have another word for closer and closer, starting with the letter A. It is approach. Remember, approach means that we have to take limits. Yes, that's why we learned limits before learning differentiation. So if we take limits and allow the 2 points to become so close to each other, hey, then the black line becomes exactly the tangent line to the green point. Yes. So Sir Isaac Newton and Leibniz were saying to each other, how small do you want to go? As close to 0 as we can. Of course, in real life they didn't say that. I just wanted to keep it lighthearted. Okay, so let's look at how we can do this. How can we implement this with limits? First of all, let's look at the 2 points. Let's start with what we know. y2 minus y1 over x2 minus x1. Okay, so let's start with x2 and x1 at the bottom over here. Instead of calling x2 and x1, we call it x and x plus h. Because the idea is very simple, right? We want to bring the 2 points closer and closer to each other. So instead of calling x1 and x2, I'm just going to call it x. And the second one is a distance of h away. So x and x plus h. Okay? Now let's look at the y coordinates. Okay? For the first one, for the green point, what do we get? Or what is the y1 called? Okay, it's called something differently. First of all, let this graph be y equals to f of x. Okay, meaning that it's a function. A function means that it behaves like a machine, which means that, hey, if I put in the input of x, yeah, I will expect an output of x. So the y coordinate of this point is very simply just f of x. So instead of y1, we're going to call it f of x. Okay, and then for y2, this is what we're going to get, yeah? Again, instead of putting in x, my input is now x plus h. So if I put in x plus h into the machine, what I get will be f of x plus h. So my y2 is going to be f of x plus h. Okay, so instead of saying y2 minus y1, we say f of x plus h minus f of x. Okay, so very simply, y2 minus y1 over x2 minus x1 is going to be f of x plus h minus f of x divided by h. Do you see this? Yeah, x2 minus x1 is actually just h. Okay, so on the next page, I'm going to write this down. Yeah, this is our rise over run. This is actually y2 minus y1 over x2 minus x1. Rise over run, or the one that students are more familiar with. Okay, but are you forgetting something? We're supposed to let the 2 points become closer and closer to each other. What is something that I can change to make them closer and closer? And remember, it's h. As h becomes smaller, then the 2 points become closer and closer to each other. So I got to include this. LIM h arrow 0. What does that mean? It means that we want to take the limit of this rise over run expression over here as h becomes closer and closer to 0. And what we have here is known as the first principles of differentiation. This is the most basic rule of differentiation. This is where everything rests on. Yeah. So this is the introduction, and you realize that, hey, differentiation is not so difficult after all. It is essentially rise over run, but with the difference that we want the 2 points, right? The rise over run of the 2 points to be very, very close to each other. Okay. So I come to the end of the video. Thank you for watching. And in the next video, we're going to go through a concrete example of how does this principle of differentiation look like in action. So until the next video, I hope to catch you on the flip-flop.